Welcome everyone. Let's begin our lesson for today by going over the learning goals and success criteria. First, what are we learning? We're learning how to construct radical numbers on the real number line, compare and contrast mathematical techniques in order to solve complex problems, evaluate your options when solving problems in order to solve problems in the simplest and most efficient way possible, to simplify radical numbers, perform various operations on radical numbers, use trigonometric properties to find ratios of side lengths of right triangles, to find the side lengths of a right triangle by using trigonometric functions, to find angle measures of a right triangle by using trigonometric functions, to utilize trigonometric functions of 30, 60, 90 right triangles, to utilize trigonometric functions of 45, 45, 90 right triangles, to use trigonometric functions to find the altitude and base of an isosceles triangle, to find the area of regular polygons, to determine the origins of the number pi, to utilize sequences and discover how sequences approach limits, to use spreadsheets to perform mathematical sequences, to determine the origins of the number e, to use logarithms to solve exponential functions, to use logarithmic properties to simplify logarithmic expressions, to recognize all numbers as being part of the number system, to determine which number set within the number system a number belongs, to recognize that numbers can belong to multiple number sets at the same time, to perform mathematical operations on rational and irrational numbers, and to determine which number set a number belongs to after operations are performed on rational and irrational numbers. How are we learning it? Through the Reasoning with Irrational Numbers review notes and the Reasoning with Irrational Numbers review assignment. When can we use this information? To cut boards into smaller equal pieces in order to create or repair furniture, to look at difficult situations in your life and evaluate your options and opportunities in order to make the best decision for your life, to determine the dimensions of a housing lot when given the square footage to determine whether or not the furniture or additions will fit, to repair the roof of your house while making sure that the roofing is flush with the house and the slope of the roof allows for water runoff, to determine the area and volume of a circular or cylindrical objects, which could help determine how much fluid a bucket or water jug can hold, to determine the dimensions of fencing around a house or when setting up fencing for pets, to use spreadsheets to calculate mathematical applications such as creating and maintaining a budget and calculating the point totals of sports tournaments, to determine how we can use number sequences to calculate potential growth in your business, to calculate your daily income based on your overall salary, to understand how number sets are affected by mathematical operations throughout the remainder of this course, and to perform simple calculations such as a budget by recognizing boundaries of numbers to determine if the items in your budget will stay within your income amount. How do you know you learned it? By getting a score of 4 on the Reasoning with Irrational Numbers review assignment. Now let's take a look at our agenda for today. We will begin by going over the learning goals and success criteria. While we do that, you'll fill out your Get It Started. Once you've completed your Get It Started, we'll go over it together and answer any questions that you may have. After that, we'll go over the Reasoning with Irrational Numbers review notes, and then I'll give you time to complete the Reasoning with Irrational Numbers review assignment. Once you've completed the assignment, we'll go over it together and answer any questions that you may have. At the end of class, we'll go back over our learning goals and success criteria while you fill out your before you go. Your only homework for tonight is to work on any incomplete assignments that you may have. Let's take a look now at the Reasoning with Irrational Numbers review notes. The notes begin with the learning goals and success criteria.
Now here's a video that shows you how to construct square root of 2 on the number line. Now the hint that you need to know is we're going to think of square root of 2 as being square root of 1 plus 1. And if we create a right triangle with legs of square root of 1 and square root of 1, then the hypotenuse should be square root of 2. And we get there by using the Pythagorean theorem. So in this case, if we can make this side length square root of 1 and the other side length square root of 1, then the line that connects them would be square root of 2. So that's how we'll do this. So you can watch the video on how to complete that.
Let's talk now about how to graph square roots on the real number line. This time we're going to talk about how to graph square root of 2 on the real number line. And what we should notice is we want to be able to create a right triangle, something like this, and make this the square root of 2. What we should notice is, in order to make this the square root of 2, if we want to use our special right triangles, this length here
should be 1. And this length here should be 1. And if that's the case, then this length here should be the square root of 2. So what we need to do is we need to go ahead and create this length also to be 1 on this side, and then once wherever they intersect, that should be square root of 2. So what we're going to do is we're going to use where it says more tools. I'm going to click on perpendicular line because I need to make sure that I have a perfect right angle. So I'm going to click on this segment here, this line here, and notice it creates a perpendicular line, and I want it to go through 1, just like that. So we know that this length is 1. If I can make this length 1 also, then the distance from here to here should be square root of 2. So let's go ahead and do that. So I'm going to use the circle tool, and if I go from this point out to this point, that means that the radius from here to here is 1, and it's also from here to here is 1. So I'm going to go ahead and put a point where they intersect, right there. So just like my drawing I made here, this segment was 1, this segment was 1, so this side here should be square root of 2. So if I connect 0 to this point here using a segment, then this should be square root of 2. Now, that's great that this is the square root of 2, but we need to bring that down to the number line. So what we're going to do is we're going to use a circle tool and go from this point to that point there, just like that. And wherever that circle now intersects, because it's still a radius of square root of 2, so this radius also is square root of 2. So wherever the circle intersects the number line should be square root of 2. So I'm going to go ahead and put a point right there, and that point right there represents square root of 2. Now we can take a look at how to construct square root of 3 on the number line. Well, we should think of square root of 3 as being the square root of 1 plus 2. So we would have legs of square root of 1 and square root of 2, and then the hypotenuse would be square root of 3. So here's a video showing you how to do that one. Let's talk now about how to construct the square root of 3 on the real number line. So on this one, we're given 0 and 1, and we're also given square root of 2. So what we should notice is, using our right triangle, if we were to create a right triangle, we should notice that using the Pythagorean theorem, if we want this side here to be square root of 3, that's what we're trying to achieve. So we'll go ahead and put that in. So if we want that side to be square root of 3, then using the Pythagorean theorem, we know that a squared plus b squared equals c squared. So the only way to get 3 is 1 plus 2, right? So if we were to take the square roots of each of those, square root of 1 is 1. So one of these sides has to be 1. So we'll go ahead and make this side here 1. And this side here would then have to be the square root of 2, which is just square root of 2. So I'm going to put square root of 2. So in order to get a square root of 3, we have to have square root of 2 for one side and 1 for the other side. Well, luckily we already have square root of 2 here. So that length is square root of 2. So now if we can just make a right angle here and then make this length 1, then when we connect the dots, that should be square root of 3. So let's go ahead and do that. So I'm going to go ahead and create a perpendicular line. So I'm going to go to more tools, and I want a perpendicular line. That'll give me a perfect right angle. So I click on this number line here, and I want it to go through square root of 2. So I click there. So there's my first part. Now I need to make this length here 1. So I'm going to make a segment that goes from 0 to 1. So now that I can use that as my radius. So I'm going to go to more tools, compass. I want this length here. So notice if I put it here at 0, it goes through 1. And I want that to go with the center at square root of 2, right there. So now I have my circle, and I know that the distance from here to here is 1. So I'm going to put a point where they intersect. So far I have my square root of 2 and my 1. Now that means that this length, according to my right triangle, should be square root of 3. So I'm going to use a segment tool to go from here to here. So this length here should be exactly square root of 3. Now from there, I need to copy this down onto my number line. So I go to circle,
and I click on this point here, and I want it to go through this point here. Notice the radius is square root of 3, so that means that in this direction the radius is also square root of 3. So wherever the circle and the number line intersect should be exactly square root of 3, so I'm going to go ahead and put a point there, and that point represents square root of 3.
Next, we will take a look at how to construct square root of 5 on the number line. And we're going to think of square root of 5 as being square root of 1 plus 4. So we would have legs of square root of 1 and square root of 4. We could also have square root of 2 and square root of 3. Either one of those works. And here's a video that shows you how to do that.
Let's talk now about how to construct square root of 5 on the real number line. So I'm going to look at this in terms of Pythagorean theorem. So I'm going to draw my right triangle over here again. So I'm going to draw a right triangle. Just like that. And I know using the Pythagorean theorem, if I want this to be square root of 5, so I'm going to go ahead and label that as square root of 5. So if I want that side length to be square root of 5, these two sides, they have to add up to be 5. So that could be 4 and 1 or 2 and 3, right? Those are the ways we can get 5. So let's say that I wanted it to be 2 and 3. So if I do that, this side would be the square root of that, so square root of 2. And the other side would have to be the square root of 3, so which is just square root of 3. So I'm going to put in square root of 3. So I can make this side square root of 2 and this side square root of 3. That would give me 5. Or I can change that and use 4 and 1 and take the square roots of each of those. So the square root of 4 is just 2. And the square root of 1 is just 1. So what I could do now is I can make this 2 and 1, and then I don't even need these square roots. So either way works. I'm going to do 2 and 1 just because it's a little easier. So now all I need to do is find where 2 is. Well, if this distance is 1, then if I copy that distance over here, it would be 2. So what I'm going to do is I'm going to use the circle tool and go from 1 out to 0 here. So I have a radius of 1 here and a radius of 1 here. So this point here, where the circle and the number line intersect, that point should be exactly 2. So now I have my 2. Now I just need to copy this and make it be 1. So I'm going to use my segment tool here to connect this point and get my radius. Then I'm going to use the compass tool to copy it over here to 2. So just like that. So now, once I draw my perpendicular line, it should have an exact length of 1. So I'm going to go ahead and go to More Tools, Perpendicular Line. I want it to be perpendicular to the number line here. And I want it to pass through 2, right there. What we should notice is we have a length of 2 here, and this length, because we use the circle with the radius of 1, this length here should be 1. So we have 2 and 1. So that means the distance from this point to here should be exactly square root of 5. So I'm going to go ahead and put a point here, and I'm going to use a segment to connect them, right there. So there we go. Now this distance here should represent square root of 5. So now all I need to do is use my circle tool to go from this point out to this point there. And this has a radius of square root of 5. So therefore, when I go down to here, I also have a radius of square root of 5. So now all I need to do is put a point where they intersect right there. And that point right there should represent square root of 5.
Now we'll take a look at how to construct 2 square root of 3 on the number line. And we're going to think of 2 square root of 3 as double square root of 3. So all we would need to do is find where square root of 3 is and then copy that distance. And here's a video that shows you how to do that.
Let's talk now about how to scale a square root now. So right here we're supposed to construct 2 square root of 3. Well, we know where square root of 3 is. It's right here. So 2 square root of 3 would just be doubling that. So all we would need to do is we can draw a circle
we go from this point here and bring it all the way back to 0 so that we have a radius here of square root of 3. Well, if we go to the other side, this is also square root of 3, so that means that the distance from 0 to out here is 2 square root of 3, because it's doubled the square root of 3. So all we need to do is put a point here, and now we have constructed 2 square root of 3. Now let's take a look at how to construct negative square root of 2 on the number line. We'll construct it by constructing square root of 2 and then copying it to the other side of 0. And here's a video that shows you how to do that. Let's talk now about how to construct a negative square root on the real number line. So in this one, we're going to create negative square root of 2. So nice thing is we've already constructed square root of 2. So from that now, if we can just copy it over to the other side, we'll have negative square root of 2. So what we're going to do is we're going to use the circle tool. We're going to click on 0, and we're going to extend it all the way out to square root of 2 right there. And what we should notice is we have a radius of square root of 2, which means that on the other side we have a radius of square root of 2. So on this side, this would be negative square root of 2 right here. So all we need to do is put a point there, and that point should represent negative square root of 2. Now let's take a look at how to construct square root of 2 plus square root of 3. So we already have square root of 2 and square root of 3. So now we just need to add them to each other. So we would take the distance from 0 to square root of 2 and add it to the end of square root of 3. And wherever that is should be square root of 2 plus square root of 3. And here's a video that shows you how to do it. Let's talk now about how to add 2 square roots on the real number line. So in this one, we're going to add square root of 3 plus square root of 2. Well, what we should notice is we have a square root of 3 here and a square root of 2 here. So what we're going to do from there is we're going to go ahead and create a segment that goes from 0 to square root of 2. So that will give me a radius. Now, if I can copy this distance over to the other side of square root of 3 over here, then that should add them together. So let's go ahead and do that. So I'm going to go ahead and use the compass tool. So more tools, compass. I want this distance here. So that gives me square root of 2. And I want to add that to square root of 3. So now on this side here, I would have square root of 3 plus this distance here, because this is the radius is square root of 2. So this distance here will be square root of 2. So this is square root of 3 plus square root of 2. Now if I wanted to subtract these and make it square root of 3 minus square root of 2, I would do the exact same thing. So I would take this distance and make this my center, but now minus square root of 2 would be over here. So if I put a point here, this would represent square root of 3 minus square root of 2. Now what are the types of roots? There's the square root, which looks like this, the square root of n, and it's some number times itself equals n. So for instance, the square root of 64 is 8, because 8 times itself is 64. So that's the square root. Then there's the cube root, and it looks like this with the little 3 over the square root symbol. And this means we're taking a number and multiplying it by itself 3 times. Fourth root is 4 times. Fourth root is 4 times, and we could keep this going. We could do the 5th root, 6th root, 8th root. As far as we want to go, we can continue this on. So now how do we simplify roots? Well, we first want to see if it's a perfect square. Well, 9 is a perfect square, so we can take the square root of that. And that's really 3 times 3, right? 9 is 3 times 3. So when we pull it out, we should pull the 3 out because it's 3 squared. So the square root of 9 is just 3. Now let's look at the cube root of 8. Well, 8 is really 2 times 2 times 2. So it is a perfect cube because it's 2 3 times, right? So it's 2 to the 3rd power. So we can pull that out, and our answer then would be 2. Now what happens if it's not a perfect square or perfect cube or whatever we're looking for? For instance, 8 is not a perfect square. Well, we can see that it is 2 times 2 times 2, right? So we do have this first part in common. This is a 2 squared times 2. So we can pull that 2 out from the 2 squared, And we're left with 2 square root of 2. Now what about the cube root of 54? Well, we should notice that 54 is really 3 times 3 times 3 times 2. So we can keep this first part because that's 3 cubed. So we can just pull that 3 out. And we're left with then the cube root of 2 over here. And we pull out the 3 here, so we end up with 3 cube root of 2. Now simplifying root expressions. So we have 3 square root of 2 plus 5 square root of 2. Well, as long as we have the same root, we can treat that like it's a variable almost. And that means that we can combine those like terms. So we'll add the coefficients and keep the variable, or in this case, keep the square root. So this becomes 3 plus 5 is 8 square root of 2. Now when we multiply, so we multiply the coefficients and then multiply the roots. So in this case we have 2 times 1 in reality, because this is 1 square root of 5. 2 times 1 is 2. And square root of 3 times square root of 5. So we end up with 2 square root of 3 times 5. And 3 times 5 is 15. So it's 2 square root of 15. Now, a couple of formulas that you'll need for today are difference of squares. So difference of squares says that we start with a plus b times a minus b. And that's equal to a squared minus b squared. And this also works in reverse. So if we started with a squared minus b squared, that's equal to a plus b times a minus b. Now how do we use difference of squares when dealing with roots? Well, what we should notice is this says 3 square root of 2 plus 5 square root of 2 times 3 square root of 2 minus 5 square root of 2. Well, we should notice that we have a and a plus b and minus b. So we can rewrite this as a squared minus b squared. So we will take 3 square root of 2 and square that minus 5 square root of 2 squared. Now when we square this, we're going to square the coefficient and square the square root. So 3 squared is 9 and square root of 2 squared is just 2. So we end up with 3 squared and square root of 2 squared minus 5 squared and square root of 2 squared. Well, 3 squared is 9. Square root of 2 squared is just 2. 5 squared is 25. And square root of 2 squared is 2. So we end up with 9 times 2 minus 25 times 2. Well, 9 times 2 is 18, and 25 times 2 is 50. So we get 18 minus 50, which is negative 32. So this is a simple way to solve without having to actually FOIL this and then multiply everything out and combine and everything. So this is just a simpler way to do it in fewer steps. This one says 3 square root of 2 plus 5 square root of 2 plus 3 times 3 square root of 2 minus 3 minus 5 square root of 2. Well, what we should notice is if we were to group this part here and this part here, it still becomes a plus b times a minus b. So if we rewrite this, this is 3 square root of 2 plus, and then 5 square root of 2 plus 3. And this is 3 square root of 2 minus 3 plus 5 square root of 2. So if we reorder these, which we could, then we see that this is our a, and this whole thing here is our b. So we can rewrite this as 3 square root of 2 squared minus 5 square root of 2 plus 3 squared. So now we can go ahead and multiply this out. So we're going to say 3 squared and square root of 2 squared. And then here we have 5 square root of 2 plus 3 squared. Now with this, we're going to have to actually FOIL it. And when we do that, we get 9 times 2 minus 50 plus 30 square root of 2 plus 9. Now we're going to go ahead and combine these. So this negative sign goes to everything. So this becomes 18 minus 59 plus 30 square root of 2. So that's 18 minus 59 minus 30 square root of 2 because the negative sign's got to carry into everything. We'll combine these. 18 minus 59 is negative 41. And we'll keep this as minus 30 square root of 2. Now, difference of cubes. Difference of cubes states that a minus b times a squared plus ab plus b squared is equal to a cubed minus b cubed. And likewise, we could go the other way and say a cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. So, in this case, we have 3 square root of 2 minus 5 square root of 2 times 18 plus 15 square root of 2 plus 50. And what we should notice is 3 square root of 2, if we square that, we get 18. And if we square 5 square root of 2, we get 50. So this is really a minus b times a squared plus 2ab plus b squared. So we can rewrite that as 3 square root of 2 cubed minus 5 square root of 2 cubed. Now we just cube these, so this is 3 cubed and square root of 2 cubed. And then we have 5 cubed and square root of 2 cubed. And when we do that, we get 3 cubed, which is 27, and square root of 2 cubed, which is 2 square root of 2. And then here we have 5 cubed, which is 125, and square root of 2 cubed, which is 2 square root of 2. So now we just combine these. So 27 times 2 is 54 square root of 2, and 25 times 2 is 250 square root of 2. Now we just combine these like terms. So we get 54 minus 250 is 196 square root of 2. Now, how do we make a critical argument? So in this assignment today, we're going to be looking at two different people's solutions to problems, and we're going to critique and decide who did it best. First of all, did they do it correctly, and which way would have been the most efficient way to do it. So, how to critique a critical argument? First thing we need to do is state how they did it. So in this case, Anne just multiplied everything out, FOILed it, and then simplified. Simon, on the other hand, used grouping and difference of squares and things like that to be able to get there. So that would be his solution. Now, next thing is, did they do it correctly? It doesn't matter if they had a more efficient way if the answer is not correct. So did they do it correctly? State if there was an easier way to complete the problem. Did they do it in the easiest way possible? And then if we're dealing with one or more students, which in this case we are, can we compare and contrast their work and decide who did it better? Now let's talk about the distance formula. Now if we're given 2 points such as A and B, and they have an x value and a y value each, the distance between the 2 points follows from the formula below. So we're given this formula, d stands for distance, is equal to the square root of the difference of the x's squared plus the difference of the y's squared. So for instance, if we had 2 points and the first point was 2, 3 and the second point was 4, 6, well, we'd say that the distance is equal to the square root of, we'll take the first one, so this is 4 minus 2 squared plus 6 minus 3 squared. Well, we can see that 2 squared is 4, and 3 squared is 9, so this is 4 plus 9 under the square root. We combine those and we get square root of 13. There is no perfect square root of 13, so we just leave it like that. Now, what are the parts of a right triangle? Well, if you notice, a right triangle has 3 sides, and this is our 90-degree angle. We call the side opposite of the 90-degree angle, or the longest side, we call that the hypotenuse. Then each of the other 2 sides we call our legs, and if we're looking at this angle here, this is considered the opposite angle. So notice it's the side that's opposite of where this angle is located. So if we drew an arrow from it, it would go straight to this side. So that's the opposite. And the side right next to it we call the adjacent side. So we have hypotenuse, we have opposite, and we have adjacent. Now, what are the trigonometric properties? The first one we call sine. And sine is the opposite side over the hypotenuse. So it's a ratio of the side lengths, with the opposite side being on top and the hypotenuse length being on bottom. Now, cosine is adjacent over hypotenuse. So we have our near side, and we'll take that length over the length of the hypotenuse. Now tangent is opposite over adjacent. So it's the length of the opposite side over the length of the adjacent side. The way we can remember this is SOHCAHTOA. So SOHCAHTOA is the easiest way to remember it. So is sine, opposite over hypotenuse. Ka is cosine, is equal to adjacent over hypotenuse. And toa is tangent, is equal to opposite over adjacent. Now how do we use these trig properties? So let's say I wanted the sine of, we call this theta. So we want the sine of theta. So sine, remember, is SOH, cosine is CAH, and tangent is TOA. So we're going to take this and we're going to go opposite, which is 4, over the hypotenuse, which is 5. So the sine of theta is 4 over 5. Now we have the cosine. So the cosine is the adjacent over the hypotenuse. So the adjacent side is here. So this is 3 over 5. And tangent is opposite over adjacent. So the opposite is 4. And the adjacent is 3. So it would be 4 over 3. Now let's look at another example. We have 1, 1, and square root of 2. So the sine of theta is opposite over hypotenuse, and the cosine is adjacent over hypotenuse, and the tangent is opposite over adjacent. So in this case we have theta here, so opposite is 1, and the hypotenuse is square root of 2, so it's 1 over square root of 2. Now cosine is adjacent over hypotenuse, so the adjacent is 1. The hypotenuse is square root of 2, so it'll be 1 over square root of 2 as well. And then tangent is opposite over adjacent, so this is opposite is 1, adjacent is 1, so it'll be 1 over 1. Now the rules of mathematics state that you cannot leave a rational number in the denominator. So we cannot leave square root of 2 in the denominator, so we need to rationalize it. So on the last slide we saw that sine of theta was 1 over square root of 2. So we need to change that. Now in order to change it, what we're going to do is we're going to multiply both top and bottom by the denominator. Because if we square anything, even if it's a square root, if we square a square root, then we get an integer out of it. So we have square root of 2 times square root of 2, which is just 2. So, and then 1 times square root of 2 is square root of 2. So we get square root of 2 over 2. It's okay for us to have a rational number in the numerator, but not the denominator. So this is the sine of theta. Now how do we find side lengths? So we're given a triangle here, and we're told that we need to find this length x. And we know that this side is 3 and this angle is 35 degrees. So first of all, we need to decide which trig function we need to use. Well, in this case, we have an angle, and from this angle, we have an opposite and an adjacent. We know absolutely nothing about this one. Even though we don't know what this is, we know that that's what we need to find. So we know the opposite and the adjacent. So the function that uses opposite and adjacent is tangent. So we're going to say that tangent 35 degrees is equal to opposite over adjacent, which is x over 3. So now we know that tangent 35 degrees is equal to x over 3. Now we need to get x by itself, so the 3 is dividing from x, so we're going to undo that by multiplying. So we multiply both sides by 3, and now we get 3 tangent 35 degrees is equal to x. Well, now we have x by itself, so we just need to plug this into our calculator. There's a link here that'll take you to the trigonometry calculator. So we're going to enter that into our calculator, 3 tangent 35 degrees. And when we do that, we should see that it ends up being 2.10 about. So this side here would be about 2.10. So that's how we can find a side length from an angle and a given side. Let's look at another example. What if this time we need to find the hypotenuse? So again, we know that this is 35 degrees, And here we have an adjacent and a hypotenuse that we can work with. So adjacent and hypotenuse would be cosine. So we'd say cosine of 35 degrees is equal to 3 over x. Well, again, we need to get x by itself, but x is being divided by, so we need to go ahead and move it to the other side first. So we'll multiply both sides by x, and we get x cosine of 35 degrees is equal to 3. Well, we still don't have x by itself, so we need to get rid of cosine 35 degrees. Well, to move this part over to the other side, we're going to divide by cosine of 35 degrees. Or another way of saying divide by cosine 35 degrees is multiply by 1 over cosine 35 degrees. So now we get x is equal to 3 times 1 over cosine 35 degrees. Now we're going to just enter that into our calculator. And the calculator link is here. So you can go ahead and click on that link. And when you enter it into your calculator, you should see that 3 times 1 over cosine 35 degrees is equal to 3.66. Let's look at one more example. So now we have that this is 35 degrees, and we know that this side is x, this side is 3. So we know the opposite, and we know the hypotenuse. So we'll go ahead and set it up. We know that with opposite and hypotenuse, that would be sine. So we're going to say sine of 35 degrees is equal to x over 3. Now we're going to get rid of this 3. So it's being divided by x, so we're going to multiply both sides by 3. And we get 3 sine 35 degrees is equal to x. So now we have x by itself, so we can enter this part into the calculator. So we'll go ahead and enter 3 sine 35 degrees into the calculator. And when we do that, we solve it and we get 1.72 as our x. There's a video here that shows you how you can use calculator.net to find side lengths. So you can go ahead and watch that video and figure out how to find side lengths. Let's talk now about how you can check your work when finding the length of a side of a right triangle when you're given one side and an angle. So let's say that in this picture we're trying to find A and we have B. We know that B is 3. And we know that angle alpha, in this case, this angle, is 60 degrees. Let's go ahead and we'll hit calculate. And it tells us what the lengths of each of the sides are and each of the angles are. So we can see that A, in this case, is 5.19615, or 3 square root of 3. And C is 6. We can also see that angle beta, this one here, is 30 degrees, and this angle here is 90 degrees. So we can use this information to help us solve for these different angle measures and side lengths. Now let's talk about inverse trigonometric properties. So inverse sine, this is what it looks like. So it's sine to the negative first power. So we call that the inverse sine. So if sine theta equals 1/2, then inverse sine of 1/2 equals theta. So it's just a way of flip-flopping it so we can solve for the angle measure using the ratio. So all we do is we change it to inverse sine and then we flip the theta and our ratio. Same thing with cosine. So we have inverse cosine. And if cosine theta equals 1/2, then inverse cosine of 1/2 equals theta. So again, change it to inverse and flip your theta and your ratio. And tangent's exactly the same thing. So we have inverse tangent. And again, tangent theta equals 1/2, then inverse tangent of 1/2 equals theta. So how does that help us find angle measures? So in this case, we want to find theta, which is this angle here, and we're given this side and this side. Well, this side is our adjacent, this side is our hypotenuse, so we have adjacent and hypotenuse, so we know that we're going to need to use cosine. So we'd say cosine of theta is equal to 3 over 4, adjacent over hypotenuse. Now, we can't solve for theta necessarily, so we need to go ahead and use our inverse cosine now. So we're going to change this to say inverse cosine of 3/4 is equal to theta. Now we can just plug this part into our calculator. So we're going to enter inverse cosine of 3/4 into our calculator. There's a link here that takes you to the calculator. And when we enter that in, we should see that it's 41.41 degrees. Let's look at another example. So this time, again, we're solving for theta, and we're given this side and this side, so we have our opposite and our hypotenuse. So we know that opposite and hypotenuse should be sine, so we should end up with sine theta is equal to 3/4. Now, this isn't going to help us. We need to get theta by itself, so we're going to use the inverse sine. So this becomes inverse sine of 3/4 is equal to theta. So we will plug in inverse sine of 3/4 into our calculator, and when we do that, we get 48.59 degrees. One more example. We have theta here, and we have that this side is 3 and this side is 4. So now we're going to go ahead and solve for theta. Now we have our opposite and we have an adjacent side, so we know that in order to do this we need to use tangent then. So it will be tangent theta is equal to 3/4. Now we can't use tangent here because that's not going to help us with theta, so we're going to need to use inverse tangent. So this will be inverse tangent of 3/4 is equal to theta. Now we can go ahead and plug that into our calculator. So we put in inverse tangent of 3/4 into the calculator, and when we do that, we should get 36.87 degrees. There's a video here that shows you how you can check angle measures in calculator.net. So you can watch this video and see how you can check your work using calculator.net.
Let's talk now about how to check our work when trying to find an angle measure of a right triangle. So in this case, let's assume we're given two side lengths and we're expected to find an angle measure. So let's say in this triangle we know that C is 6 and we know that B is 4. And let's say that we're trying to find angle alpha in this case, this angle here. Well, we put it into the calculator, B is 4 and C is 6, and we hit calculate. And notice it's going to tell us everything else we need to know. So we can see that A in this case would be 4.47214, or 2 square root of 5, which is fine. That's not what we were looking for. What we were looking for was angle alpha. Well, we can see that angle alpha is 48.19 degrees. Angle beta, if that's the one we were trying to find, was 41.81 degrees. And we know that angle C here, this angle here, would be 90 degrees because it's a right triangle. So we can check and find any other missing information using this right triangle calculator. Now let's talk about what a 45, 45, 90 degree triangle looks like. So what this means is we're going to have our 90 degree angle here, and each of the other two angles will be 45 degrees. And because these two angles are exactly the same, that means that the side lengths opposite of them should be the same. So we're going to treat this as a unit. So this will be 1, and this is 1. So these two sides are the same. So now this side here, using the Pythagorean theorem, will be square root of 2. So 45, 45, 90 degree triangles tell us that we should have 1, 1, and square root of 2 as our side lengths. Now 30, 60, 90 degree triangles. So if this angle is 30, and obviously this angle is 90, that means that this angle here has to be 60 degrees. And the rule is that the side opposite of the 30 degree angle should be 1. The side opposite of the 60 degree angle should be square root of 3. And the side opposite of the 90 degree angle should be 2. So for a 30, 60, 90 degree triangle, we should have 1, square root of 3, and 2. Now if we know that this one's 60 and this one's 30, then this one's obviously 90. So the side opposite of here should be square root of 3. Side opposite of here should be 1. And this side should be 2.
So that's how this would work with a 60, 30, 90 triangle. Now, how do we use our trig properties on these? Well, if we have that this one's 45 degrees and this one's 1, we know that sine is opposite over hypotenuse. So if this is 45 and we have opposite, which is this case, we know it's going to be 1 and this is going to be square root of 2. So it's 1 over square root of 2. And now, even though we didn't know what either of these sides were, because we know that this is 45 degrees, we know that this is 1 over square root of 2. Cosine now. Cosine is adjacent over hypotenuse. So the adjacent side, in this case, we do know that that's 1. And the hypotenuse now, because it's a 45, 45, 90, should be square root of 2. So it's 1 over square root of 2. Now we know tangent is opposite over adjacent. So we know that the opposite is 1. The adjacent will also be 1 because these should match. So we get 1 over 1. Now what if we scale it? So what if this side length is not 1? Well, all we do is we take whatever this is and we multiply it by whatever we're supposed to have. So in this case, this should be 1, but it's 4. So we multiplied 1 by 4 to get there. So we'd multiply this one by 4 and this one by 4 as well. And what we end up with is opposite over hypotenuse. So this side length should be 1, but we're scaling it by 4. So 1 times 4 is 4. So we should end up with our opposite being 4. And our hypotenuse should be square root of 2, but we multiplied by 4. So it should be 4 square root of 2. So we should end up with 4 over 4 square root of 2. Now here, we're doing cosine, which is adjacent over hypotenuse. So this side should be 1 as well, but it's 6. So we had to multiply 1 times 6 to get there. So we're going to multiply everything by 6. So this side should be 6 as well. This side should be 6 square root of 2. So when we do the cosine of 45 degrees, we should have 6 over 6 square root of 2. Now tangent is opposite over adjacent. So the opposite in this case is 8. It's supposed to be 1 though. So we multiplied by 8. So this side should also be 1 times 8. And this should be square root of 2 times 8. So this should be 8 and this should be 8. So we end up with tangent of 45 degrees is equal to 8 over 8. Now let's look at 30, 60, 90 triangles. So remember 30, 60, 90 should be 1 square root of 3 and 2. So remember that sine is opposite over hypotenuse. So we're going to take this opposite, which is 1, and the hypotenuse, which should be 2. So we end up with 1 over 2. Now cosine. Cosine is adjacent over hypotenuse. So if this side is 1, we know that this side should be square root of 3, and this side should be 2. So the adjacent side is square root of 3, and the hypotenuse is 2, so it should be square root of 3 over 2. Now tangent. Remember, tangent is opposite over adjacent. So the opposite side is 1, and the adjacent side should be square root of 3. So we should be 1 over square root of 3. Now what if we scale it? So this side here is 4, but it should be 1. So we multiplied it by 4. So now this side should then be 4 times square root of 3. And this should be 4 times 2, which is 8. So if we take the sine, remember sine is opposite over hypotenuse. So the opposite is 4. And the hypotenuse is 8. So we should get 4 over 8. Now cosine. Remember cosine is adjacent over hypotenuse. So the adjacent side is here. And we scaled it by 6. So it should be 6 square root of 3. And our hypotenuse should be 2 times 6, which is 12. So we should get 6 square root of 3 over 12. Now this one we've scaled by 8, and we're trying to find the tangent, which is opposite over adjacent. So if this is scaled by 8, then we have to scale this one by 8 as well. So that's 8 times square root of 3. So we should end up with the opposite, which is 8
over 8 square root of 3. And those should be our answers. Now what if we're given the 60 degree here? So again, it's the same thing. This just becomes our 30 degree angle. So this is 1. This should be square root of 3, and this should be 2. So let's go ahead and do that. So now we want the sine of that 60 degree angle. So the sine is opposite, which in this case is square root of 3. And hypotenuse is 2. So we end up with square root of 3 over 2. Now cosine, remember that cosine is adjacent over hypotenuse. So we're finding this 60 degree angle. This one's our 30. So 60 degree, the adjacent side is 1. And the hypotenuse should be 2. So it should be 1 over 2. And tangent, remember, is opposite over adjacent. So the opposite is square root of 3. The adjacent is 1. So it would be square root of 3 over 1. Now what if we were to scale these ones? Well, same thing. So this is our 30 degree angle. So the opposite of the 30 degree angle should be 1. But it's 4. So we're going to scale everything by 4. So this becomes 4 times square root of 3 here. And this becomes 4 times 2, which is 8. So the sine of 60 degrees then is opposite over hypotenuse. And the opposite side should be 4 times square root of 3, which is 4 square root of 3, over the hypotenuse, which is 4 times 2, which is 8. So we end up with 4 square root of 3 over 8. Now here, same thing. We scaled it by 6 this time. So now this side should be 6 square root of 3, and this side should be 2 times 6, which is 12. So cosine is adjacent over hypotenuse. So the adjacent side is 6, and the hypotenuse is 6 times 2, which is 12. So we end up with 6 over 12. Tangent is opposite over adjacent. So the opposite side, this time we scaled by 8. So the opposite side should be 8 square root of 3. And the adjacent side should be 8. So we get 8 square root of 3 over 8.
Now what is an inscribed polygon? An inscribed polygon is a shape inside of a circle in which all the points are on the circle. So if we look here, we have some kind of a four-sided figure here, and every point falls on the circle. This is an inscribed polygon. Now what is a regular polygon? A regular polygon is a shape with all the sides and angles being exactly the same. So in this case, we have an inscribed regular polygon. So there's 1, 2, 3, 4, 5, 6 sides. And notice all the sides should be exactly the same length. And all of the angles are the same. So this angle is 60 degrees, this angle is 60 degrees, 60, 60, 60, 60. And each one of these angles is all 120 degrees. So these are regular polygons. Now, in this case, we're given a regular polygon inside of a circle. So we have a square in this case. And the question is, if we were to connect all these dots, how many isosceles triangles would we have? So if we connect the dots through here, so we draw from the center to each point, notice now we end up with 1, 2, 3, 4 triangles. So what we should notice as we go through this is the number of isosceles triangles is equal to the number of sides. So there's 4 isosceles triangles. Now what is the angle measure of each of these angles? So the angle measure is equal to 360 degrees, because there's 360 degrees in a circle. So 360 divided by the number of triangles, which in this case is 4. So if we divide 360 by 4, we get 90. So the angle measure is 90 degrees. Now what is the length of the base? How far from A to B? So if we look at one of these triangles here, we'll just look at one at a time. So the length of the base, each of these sides is 1, because we're assuming that this is a unit circle, so that means the radius is 1. So if each of these is 1, then we can figure out what this base is based off of that. Well, in order to do that, we're going to need to be able to cut this in half. So now we have a right triangle here. So this side is 1. We don't know this side and we don't know this side yet. We know that the angle measure here is half because we started out at 90 and we cut it in half. So half of this would be 45 degrees. So each of these angles here is 45 degrees. So we end up with half the base length being sine 45 degrees. So that means then that the full base length would be double this. So that's 2 sine 45 degrees. So that's the length of our base. And when we plug that into our calculator, we get 1.41421. Now we need to find this side length. Well, we should notice this is 45 degrees, and this is 1. So we need this side, which is the adjacent side. So we can use cosine to find that. So it's cosine of 45 degrees is equal to a over 1. And remember, anything divided by 1 is just itself. So we just end up with cosine of 45 degrees. And when we plug that into our calculator, we end up with 0.70711. Now we can find the area of each one of these triangles. So the area of a triangle is 1/2 the base times the height. So that's 1/2 of this, the base, times the height or the altitude here. So we get 1/2 of 1.41421 times 0.70711. And when we enter that into our calculator, we get 0.5 as our area. So each of these triangles has an area of 0.5. Well, the area of the polygon then is 4 of those because there's 4 triangles. So 1, 2, 3, 4. So if we multiply 0.5 times 4, we get 2. So that's how we can fill in our table for a 4-sided figure. Now let's look at a 6-sided figure. Well, we're going to do it the same way. So we connect all the dots. So now, how many triangles did we end up with? Well, we ended up with 1, 2, 3, 4, 5, 6. So like I said earlier, the number of isosceles triangles is equal to the number of sides. Now, what's the angle measure? Well, we're going to take 360 degrees and divide it by the number of triangles. So we get 360 divided by 6, which is 60 degrees. Now we're going to find the length of the base. So we're going to pick out one of the triangles. We'll pick this one. And we know that each of these sides is 1 because we're working with the unit circle. So that means that each of the radii are 1. So now, if we draw a line to split this in half, that'll give us our altitude, and then we can find this part of the base and this part of the base. So when we split it, we end up with 60 degrees being split in half, which is 30 and 30. So now we can go ahead and find the base using our sine function. So we know that 1/2 of the base, because all we get is this part here, so 1/2 of the base is equal to sine of 30 degrees. So that's equal to 1/2 the base. Now, if we want to find the full base, we need to multiply it by 2, because these two are exactly the same. So now it would be 2 sine 30 degrees is equal to the base. When we enter that into our calculator, we get that the length of the base then is 1. Now we need to find the altitude, which is this side here. Well, this one is the adjacent over the hypotenuse. So we would do cosine of 30 degrees. And the cosine of 30 degrees, if we put that into our calculator, we get 0.86603. Now we want to find the area of this whole triangle here. So if we do that, the area is 1/2 base times height. So it's 1/2 the base times the altitude. So that's 1/2 times 1 times 0.86603. And when we put that into our calculator, we end up with 0.43301. And now to find the area of the polygon, we need to multiply it by the number of triangles that we have. So we have 6 triangles total. So we're going to multiply 0.43301 by 6. And when we do that and put that into our calculator, we end up with 2.59808. First, what is a number sequence? A number sequence is a list of numbers that are linked by a rule. All numbers in the sequence must follow the same pattern. So for instance, if I said 1, 2, 3, 4, 5, you could continue that pattern without me actually giving you the next numbers. You could continue that on because there's a given sequence. So all the numbers in the sequence follow the same pattern. These patterns can continue on infinitely, but the rule will never change. So we could keep going and going and going, and it'll keep going, but it won't change the rule. Now, how do we do activity 2D1 part A? So the first part says, consider the sequence of numbers a sub n, whose terms are given by a sub n equals 1 plus 1 over n to the n power. So in this case, we're told what numbers to start with. So we have n being 2. So we plug 2 in for both places. And we can see then that 1 plus 1 half is 3 halves to the second power. So 3 to the second power is 9. And 2 to the second power is 4. So we should get 9 over 4 is our answer for this one. And we could continue to solve this. And when we do that, we should notice that these numbers start to look like this. Now, what pattern do we notice? Well, we should notice that we started out and we're making 0.03 jump. Now we're making 0.1 jump. Then we're making a 0.1 jump again about, and we're getting, each time our jump is getting smaller and smaller. So that means we're approaching some kind of number. So we're approaching some kind of limit at some point. So then there's a certain number that our number sequence is approaching. We don't know what it is yet, but there's some number that we're getting really close to. Here's a video that shows how you can use a spreadsheet to help you solve this sequence and figure out what number we are approaching. Let's talk now about how to fill in the number sequences approaching E spreadsheet. Now, the nice thing about this spreadsheet is most of the hard work has been done for you. So in this case, we have our n value here, and we want to find the sum and then a sub n. This is what we're ultimately trying to find, is a sub n. Now, all you need to do is this. This formula is already placed here, so you're going to go to this box here, and you're going to copy this one. So I'm going to copy this. So I right-click and hit copy, and I'm going to go here and put equals, and then I'm going to paste it. So right-click and click paste, and notice it places that exact formula right here, and I click enter. It asks if I want to do the suggested autofill. I'm going to click the check mark, and notice now it filled in all the boxes for me. So I can see exactly what this function is doing as it approaches infinity, right? As it goes from 0 all the way to 200 in this case. Then I'm going to go back, and I want to know what a sub n is. This is what I actually want to know. So I'm going to go ahead and do the exact same thing. So I'm going to copy this. So I'm going to right click and copy it. And I'm going to go here and put equals, and I'm going to paste it. And notice it places the formula there. I hit enter, and notice it autofills and makes that 2. And I'm going to go here and hit the check mark to autofill the rest of them. And notice now I can see exactly what this function is doing. As it gets bigger and bigger, it's approaching 2.71, somewhere in there. And I could keep this going. I could make this 1,000. And I'm just going to copy this and paste it. I'm going to copy this and paste it. And notice again, I can see how this is continuing to trend as we go through. So that's how you do the first part of your spreadsheet. Let's look at another example. So now we are considering the sequence of numbers s sub n, which means we're calculating a sum, whose terms are given by s sub n is equal to the sum, as k goes from 0 to n, of 1 over k factorial, where that's equal to 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial. So what you're going to do is you're going to enter this one into your spreadsheet as well and solve, and as we do that, you should notice that the pattern starts to look like this. And we should notice that we're approaching some number around 2.71, And as you continue this on, the numbers are going to continue to get closer and closer to that value. And it's very similar to the number that we were just looking at on part A. So what do we notice? Again, the values are approaching some number. The change is getting smaller and smaller and smaller each time. So that means we're getting closer and closer to some number. Here's a video as well that shows you how to enter these values into a spreadsheet so that you can check and see what number this sequence is approaching. Let's talk now about how to complete the number sequences approaching E spreadsheet. This is the second tab, so this would be for group B. And the nice thing is the formulas are already given to you. Now notice the 0 row is already filled in, so we're going to begin this at row 1. So we're going to do the same thing like we did on the previous one. So we're going to copy this. So I'm going to right click and copy it. And I'm going to go here and put equals, and then I'm going to paste it here. And then I hit enter. It asks if I want to autofill. I'm going to click the check mark to say yes, I would like to autofill. And notice as we get lower and lower, our numbers get closer and closer to 0. Now here, we're going to do the same thing. So we're going to copy this. And I'm going to put equals. And I'm going to paste it here. Right click and click paste. It asks if I want to autofill this one. I click yes. And notice now, again, my numbers are getting closer and closer. As I get to 270, okay, the numbers just become insignificant. That's why it does that. But as you can see, as the numbers get bigger and bigger, we get closer and closer to 2.718. So you'll use this table to fill in your Desmos activity. Now, how do we recognize n behavior? Using a graph or a table, we can see that as the values for n get larger, the resulting value from the number sequence can do one of these things. So basically what this is saying is, as we continue these sequences, one of three things is going to happen. We're either going to keep going to infinity. So an example of this would be 2 to the n. So as n gets bigger, 2 is going to continue to expand and expand and expand and expand, and it's going to continue out towards infinity. So it's going to get extremely large, and it's never going to stop getting larger. We could go to negative infinity, which means we're going to get smaller and smaller and smaller, and the gap is going to continue to grow, and we're going to get small, small, small forever. Lastly, we could approach some value. For instance, 1 over n. The smaller n gets, the closer we get to some number, which in this case is 0. Because 1 over 1,000 is close to 0. 1 over 10,000 is even closer to 0. So the numbers are getting closer and closer and closer to 0 as we go. So these are different ways we can recognize n behavior. First, what is a logarithm? A logarithm is a mathematical operation that determines how many times a certain number, called the base, is multiplied by itself to reach another number. So it's just another way of doing an exponential function. So this sounds like the similar definition to an exponent. So how do we rewrite logarithms as powers? So we have log base 3 of 9. That's the way we read this. So log base 3 of 9. So in order to simplify this expression, we must rewrite as a power. So really what this means is we're saying 3 to some power, which we don't know, is equal to 9. So how many times do we multiply 3 by itself to get 9? Well, we know we multiply 3 times 3 to get 9. So that's 3 times itself twice. So x then is equal to 2. Now we have log base 2 of 4. So we need to rewrite that as a power. So really this is saying 2 to some power is equal to 4. So we rewrite that as 2 to the x power is equal to 4. Well, we know that 2 times itself twice equals 4, right? Because 2 times 2 is 4. So x in this case would be 2. All right, so let's actually simplify a few of these. So it says log base 3 of 27. So we're going to rewrite that as 3 to the x power is equal to 27. So we don't know what x is yet. So we're saying that 3 times itself a certain number of times equals 27. Well, in this case, we can see that 3 times 3 times 3 equals 27. So that's 3 to the third power. So in this case, x equals 3. Now, log base 2 of 16. So that's really saying 2 to the x power is equal to 16. So how many times do we need to multiply 2 times itself to get 16? So if we go 2 times 2, that's 4. Times 2 is 8. Times 2 is 16. So that was 4 times we multiplied. So x equals 4. Now what if we're using negative power? So in this case we have log base 4 of 1/4. Well, we can see we went from an integer to a fraction. So anytime we do that, that means we have to have a negative power. So what we're really saying here is 4 to the x equals 1/4. So notice we went from an integer to a fraction, so we need to use a negative power. So what we need to look at here is, as long as this is 1, then we're good. We just need to look at this denominator and see 4 to what power equals 4? Well, 4 to the first power equals 4, so we know it's going to be 1. And because it's in the denominator, we're going to take it and make it a negative power. So this would be 4 to the negative first power equals 1/4. So x equals -1. Now here we have log base 1/2 of 4. So we're saying 1/2 to the x power is equal to 4. Well, we're going from a fraction to an integer, so anytime we do that, that means we had to flip it. So we're going to have a negative power. And then we just need to look, 2 to the what power equals 4? Well, 2 to the second power equals 4, so it would be 2. And then we just need to make it negative so that it flips. So we get x equals -2. Now, what about fractional powers? So in this case, we have log base 9 of 3. So that's really saying 9 to the x power is equal to 3. Well, notice we start with a bigger number than we end with. So that means that we have to be taking a fractional power of some kind. So 9 to what power equals 3? Well, if we take this is really the square root of 9 is equal to 3. So when we raise it to a power, it's really the 1/2 power. So in this case, x equals 1/2. Now here we have log base 32 of 2. So really that's 32 to the x power is equal to 2. Again, the number we start with is bigger than what we end with. So we know that it's got to be a fractional power of some kind. So 32 to what power equals 2? Well, we can look at it this way. 2 to what power equals 32? So 2 to the second is 4, and then 8, then 16, then 32. So that was 5 times. So we know that 2 to the fifth power is equal to 32, so that means 32 to the 1/5 power equals 2. So x equals 1/5. Now, the logarithmic property of multiplication. So what this says is log base a of b times c. If we can break that up into multiplication, then we can rewrite it in a way that's a little more easy to see. So we have log base a of b times c, and that's equal to log base a of b plus log base a of c. So we can rewrite that as addition. So what does this look like? So let's look at log base 3 of 27. Now we could do this easily and say that 3 to the third power is equal to 27, so it's equal to 3. But let's say we don't know that. Let's say 27 is too big of a number and we need to break it up a little bit. So we can rewrite this as log base 3 of 9 times 3, because 27 is equal to 9 times 3. Then we can rewrite this as log base 3 of 9 plus log base 3 of 3. Now, we can look at this and say 3 to the what power equals 9? Well, we know 3 to the second power equals 9. And 3 to the first power equals 3. So that's 2 plus 1, which is 3. Now we can check this by just doing the logarithm. So 3 to the 27th. So that means that 3 to the third power is equal to 27, which is the same as what we ended up with here. Now, what if we end up with remainders? So we have log base 3 of 18. Well, when we do this, we recognize that 3 doesn't necessarily go directly into 18, right? We can't multiply because 3 times 3 is 9, times 3 is 27. So we can't actually get all the way to 18, but we can get something out of this. So we're going to rewrite this as log base 3 of 9 times 2. So now we can rewrite this as log base 3 of 9 plus log base 3 of 2. And this part we can simplify. So log base 3 of 9 is the same thing as 3 to the x power is equal to 9. Well, we know that 3 to the second power is equal to 9. So we end up with 2 plus log base 3 of 2. We can't simplify this because we can never go from 3 to 2 by multiplying by powers. So we just leave it just like this. Now here we have log base 4 of 48. So we're going to rewrite this as log base 4 of 16 times 3. And you could do 4 and pull that out, and then you would recognize that there was another 4 that you could pull out as well. So you just keep adding stuff in. But the simplest form from in the beginning is to make this log base 4 of 16 times 3. So we can rewrite this as log base 4 of 16 plus log base 4 of 3. Now 4 to what power equals 16? We should notice that 4 to the second power equals 16. So this is really 2 plus log base 4 of 3. We can't simplify this because 3 is not any kind of a power of 4. So we'll just leave it just like this. So 2 plus log base 4 of 3. Now division property. So we could also write these as division. So we could look at it that way, or this especially works well if our part here is a fraction. So we have log base a of b divided by c. And when we rewrite that, we can say that that's also equal to log base a of b minus log base a of c. So let's take a look at how this works. So we have log base 3 of 1/9. And if we remember back to what we did earlier, we should see that this is -2 should be our answer. So let's see if that's true based on the rule we just learned. So we have log base 3 of 1 over 9. So this is really log base 3 of 1 divided by 9, because that's what a fraction says. We can break that up then and say log base 3 of 1 and log base 3 of 9, and we're subtracting those. So now 3 to what power equals 1? Well, we know anything to the 0 power is equal to 1. So 3 to the 0 power equals 1, so that's 0. And then 3 to the second power equals 2. So we end up with 0 minus 2, which is -2. Now, if we were to just do it based on this, the way we learned it originally, we said 3 to some power equals 1/9. So this is 3 to the x power is equal to 1/9. We know that it turned into a fraction, so therefore it's going to be negative. So 3 to what power equals 9? Well, 3 to the second power equals 9. And then we make it negative, so it's -2. So we can check our work and see that these two match. Now how do we do this with remainders? Well, in this case we have log base 3 of 2/3. So we're going to rewrite this as log base 3 of 2 divided by 3. So just like this. Now we can break this up and say log base 3 of 2 minus log base 3 of 3. We can't multiply 3 by itself any number of times to get 2, but we can do it here. We can multiply 3 by itself one time to get 3. So we end up with log base 3 of 2 minus 1. Now this one, log base 5 of 25 over 3. So we can take this and say log base 5 of 25 divided by 3. And then we can break this up. So this is log base 5 of 25 minus log base 5 of 3. Well, this first part, we can look at 5 to what power equals 25? Well, 5 to the second power equals 25. So this is 2. And we can't multiply 5 times itself any number of times to get 3. So we just leave that part as is. So this becomes 2 minus log base 5 of 3. Now there's a video here that shows you how you can check logarithms using Symbolab. So you can go ahead and watch this video. Let's talk now about how to use the logarithmic equation calculator to check your work when dealing with logarithms. So let's say that we were given log base 2 of 8. So log base 2 of 8, and we needed to solve this. Well, we can go ahead and enter that in and click go. And it tells me exactly what the answer is. It says log base 2 of 8 is 3. And it gives me steps to show me exactly how that works. So that's one way you can check just a simple logarithmic equation. Now let's say there was more to it. So let's say it was log base 2 of 8 plus log base 3 of 9. Well, we can go ahead and click go again. And this time it tells me that the answer is 5 because log base 2 of 8 is 3 and log base 3 of 9 is 2. So therefore the answer is 5. We can also do something like this, log base 2 of 32, and click go. We can also do something like this, log base 2 of 40, and click go. And this time it'll tell us, it gives us a decimal answer, but it also will tell us, using the log rule, that it's 3 plus log base 2 of 5. So we can do it that way as well. And this is how you can check your work using the logarithmic equation calculator on Symbaloo.com. Let's talk now about how we can change the base of a logarithm. So we have log base a of b, and let's say we wanted to change the base to c. Well, what we do is we just make it c, so we're going to change our log base to c, and that's equal to log base c of b over log base c of a. So we can change the base anytime we want to anything we want to as long as we follow this formula. Let's look at an example. So we have log base 3 of 18. Let's say we want to change the log base to 9. The way we do it is we would change this to log base 9 of b, which is 18, over log base 9 of a, which is 3. So it should look something like this, and then we can simplify. Now, let's look at this one. This one says log base 4 of 48. So let's say we want to change it to log base 8. So we would change this to be log base 8 of 48, which is b, over log base 8 of a. So log base 8 of a would be 8 of 4. So we end up with log base 8 of 48 over log base 8 of 4. So this is how we can change the base of any logarithm. Now, logarithm expressions using substitution. So let's say we were told that log base 3 of 8 is equal to a and log base 2 of 3 is equal to b. And we're asked to rewrite log base 3 of 16 in terms of a and b. So in this case, we already have something that looks kind of like this, right? We already have log base 3. So we're just going to leave it as it is and don't change the base. And we're just going to see if we can simplify this. Well, what we should notice here is that we have log base 3 of 16. Well, that's kind of close to log base 3 of 8, right? That's really 8 times 2. So let's go ahead and change this to be 8 times 2. That way we can pull out that log base 3 of 8. So really, when we rewrite this, we can say that log base 3 of 8 plus log base 3 of 2 is equal to the same thing as this. So now we have log base 3 of 8, which in this case is a. So we can rewrite that as a. So that's a plus log base 3 of 2. Now, we're not allowed to leave anything saying log because it has to be in terms of a and b only. Because it has to be in terms of a and b only, it can have numbers attached, but it's got to be in terms of a and b and any integers. We can't have anything that says log. So we get to here and we can see that we run into a roadblock, right? 3 can't be multiplied by itself any number of times to get 2, so we can't get an integer. It doesn't look like this, but it does look similar. So if we change the base to base 2, we'll be kind of close. So let's go ahead and do that. So this will be log base 2 of b, which is 2, over log base 2 of a, which is 3. So now we should notice that 2 to the first power is equal to 2. So this is really a 1. And this here is b, right? Because log base 2 of 3 is b. So this is just 1 over b. So now we rewrote it in terms of a and b. So this is a plus 1 over b. Let's look at another example. We have log base 3 of 1/2. So we start with log base 3 of 1/2. That looks kind of like this, but with the wrong base. But let's go ahead and rewrite this. So this is really division, so we can rewrite that as 1 divided by 2, which then we can break up into subtraction. So this is log base 3 of 1 minus log base 3 of 2. Well, log base 3 of 1 is really just 0, right? Because anything to the 0 power equals 1. So this is really 0 minus log base 3 of 2, which again looks very similar to b, but we have the wrong base, so we need to change the base. So this is really negative log base 3 of 2, and we're going to rewrite that with a change of base. So when we change the base to 2, this is log base 2 of a, which is 2, over log base 2 of a, which is 3. So now 2 to the first power is equal to 2, so this is 1. And this is really just b, so this is negative 1 over b. So that's how we can use the substitution to solve these things. Now we're going to be looking at, in this case, Arthur's proof of how he was able to solve this logarithmic expression. And what we're going to do is create an argument of the validity of his proof. So how do we create a critical argument? First thing we do is state how he did it. So we're going to talk about what he did. So what are the steps that Arthur did to get from here all the way down to here? Next thing is determine whether he did it correctly or not. So did Arthur even do this proof correctly? Next thing is state if there's an easier way. So as we look through this, was there a way that Arthur did things that he could have done things even easier? So for today's assignment, you're going to be creating an argument to determine whether Arthur and other people did things in the most efficient way, and did they do things correctly. Now let's take a look at part A of your activity for today. So it says, consider the sequence of numbers a sub n whose terms are given recursively. a1 is equal to 1, and an is equal to 1 plus 1 over a to the n minus 1. Well, it follows this pattern here, and this becomes pretty complicated as you go through it. But if you solve these, we should notice that a3 is 1.5, a4 is 1.6 repeat, a5 is 1.6, and a6 is 1.625. We should notice is the leap from here to here is a little bit large. It gets smaller and smaller and smaller each time, and we're getting closer and closer to something around 1.6. So we should notice that we're approaching some kind of number around, in this case, 1.62, something like that. Now to further this, there's a video here that shows you how you can enter this into the spreadsheet. So you'll go ahead and watch this video and then enter those values into the spreadsheet and see what this is getting closer to. So go ahead and watch this video. Let's talk now about how to complete the number sequences and number systems spreadsheet. So we're going to be looking at group A, and we're given this here. We're given the function that we need to input, and we're told that 1, when n is 1, a sub n is also 1. So what we're going to do is we're going to copy this. So I right click and copy it, and I'm going to go here and put equals and paste it. And I click enter, and I'm going to do it again.
I'm going to copy this. If it doesn't ask you to autofill, this is how you do it. If it does ask you, then just click the check mark. And I'm going to highlight and go all the way down to the end. And I'm going to paste it here. So I pasted it for all of them. And as you can see, it tells me that a sub n, as n is getting really big, a sub n is starting to approach 1.618-ish, right? And notice after a while, the number stopped changing. It's approaching some repeating decimal that goes on forever. Now, once you do this in your spreadsheet, you'll copy and paste your answers into Desmos. Now let's take a look at part B of your activity. So we're now going to consider the sequence b to the n, where b1 is square root of 12 and bn is square root of 12 plus b to the n minus 1. And it follows this pattern here. So when we solve this, we go ahead and enter those in, and we can see that b3 is 3.9915, b4 is 3.998, b5 is 3.99, and b6 is 3.99999. And if you notice, we're getting really close to 4, so we should be approaching some value. And we'll go ahead and check this on our spreadsheet. So there's a video here that shows you how to enter these values into the spreadsheet and see what we're getting closer to. So go ahead and watch this video. Let's talk now about how to complete the number sequences and the number systems spreadsheet. And this is the part for group B. So this is the second tab. And we're given the function already here. So we're told that these are the n's. This is a sub n. What we're going to do now is we're going to copy this. So I'm going to right click and copy. And I'm going to put equals. And then I'm going to paste it. And notice the function appears here. I hit enter. It asks if I want to autofill. I'm going to click the check mark to autofill. And notice now it fills in all the answers for me. And as I scroll down, I should see that after a while the numbers stop changing and they just stay at 4. So as this sequence continues, the values are going to get really close to being 4. So you'll enter this information into your spreadsheet, and then you'll copy and paste this into your Desmos activity. Now let's talk about the types of number sets. So the first thing we talked about before was the natural numbers. Remember, the natural numbers have a symbol of n, and they are really the counting numbers. So where did you begin to count? We began with 1, 2, 3, 4, 5, etc. So those would be some examples. Now, once we learned our natural numbers, the next thing we learned was that there's a number before 1, and that was 0, and we call those the whole numbers. The symbol for whole numbers is n0, and our examples would just be 0, 1, 2, 3. So it's all the numbers we learned before plus 0. After that, we learned that there were numbers on the other side of 0. So there were integers. And the symbol for integers is z. And our examples would be -2, -1, 0, 1, 2. So it's just the negative versions of our whole numbers. After that, we learned about rational numbers. We learned that there were numbers between 1 and 2, and between 0 and 1. And the symbol for rational numbers is q. And those include fractions. So 0, 1/2, 1/3, 1. And it also includes the negative ones as well. So it could be -1/2, -1/3, -1. After we learned about rational numbers, we learned that there were numbers that go on forever. They don't fit into any perfect fraction. So we call those the real numbers. And our symbol for that is r. Some examples of that would be 0, 0.2 repeat, pi, e. Any of those would work. Those are all real numbers. And then lastly, we learned that there were complex numbers or imaginary numbers. And the symbol for that is c. And those include our i's and our square roots of -1. Now, determining the elements of a number set. So we're going to be given things like -2, and we have to decide what number set do they belong in. Well, we know that -2 belongs in the integers because it's a negative value. So this would be
in z, or the integers. Now we have log base 9 of 3. So it's a log. We can't just leave it as a log and determine which set it belongs to, so we need to simplify this. So this is really 9 to what power equals 3? Well, we know that it's 9 to the 1/2 power equals 3 because it's a square root. So this is really 1/2, and 1/2 is a rational number, so it belongs in the set of rational numbers, or Q. Now we have 4 pi. 4 pi is an irrational number, or in other words, it is a real number. So multiplying by 4 doesn't change that, so it's really just equal to 4 pi, and therefore this is in the reals. Now we have sine of 45 degrees. Well, if we remember using our special right triangle, sine of 45 degrees is opposite over hypotenuse, and the opposite side would be 1, and the hypotenuse would be square root of 2, so it's 1 over square root of 2. Or when we rationalize the denominator, that's square root of 2 over 2. And notice we have a square root here that it's not a perfect square, so therefore it is a real number, so this is contained in the reals. So we need to talk first about what are the different types of true statements. So the first kind is always true, meaning that there is no situation in which the statement is not true. For instance, the sun will come out today. Well, there's different variations of how bright the sun might be, but the sun does come out every day. That's always true. So there are no examples that can make the statement not true. So that's always true. Then there's sometimes true. Sometimes true means that there are examples of it being true and examples of it not being true. An example of this would be, it's going to rain today. Well, could it rain today? It absolutely could, but it also might not. So sometimes it rains, sometimes it doesn't. So there are examples that make it true and counterexamples that make it false. And the last one is never true. And never true means that there are no examples when this could be true. For instance, the sun will not come out today. Well, that's never true. The sun always does come out. So examples of true statements, we have the sun comes up in the morning. Is that sometimes true, always true, or never true? Well, we should know that no matter what, the sun always does come out. So that is always true. It will be raining tomorrow. Well, tomorrow it could rain, it might not. Sometimes it does, sometimes it doesn't. So that is sometimes true. And the temperature tomorrow will be 200 degrees Fahrenheit. Well, it might feel like 200 degrees. It might feel really hot, but it will never actually get to 200 degrees Fahrenheit. So that is never true. Now let's look at some mathematical examples of true statements. So quadratics, meaning the U-shapes, increase infinitely. Is that sometimes true, always true, or never true? Well, we know that the graph forms a U like this, but it could also go down like this. So it won't always increase infinitely. Sometimes it will also decrease infinitely. So this one is sometimes true. Now this one says absolute values have negative y values. Remember, absolute values form the v. And if we take the absolute value of x, it's always going to be positive, right? So it can never have any negative values. So this is never true. And the last one says linear functions have both positive and negative y values. Well, as long as it forms a straight line, it will always be true. It will always go below the y-axis and above the y-axis. So no matter which direction it's going. So this one is always true. Now a couple words that you'll need to know for today's assignment. The first one is sum. A sum is the result of adding. So we're adding two values together. The result is the sum. Difference means we're subtracting. Product means we're multiplying. And quotient means that we are dividing. So here's some examples of what we're talking about. So it says the sum of a rational number and a rational number is rational. And we need to decide, is that sometimes true, always true, or never true? Well, if we add a rational number and a rational number, so that's a fraction and a fraction. If we add two fractions together, will we ever get anything that's not a fraction? Well, we know from closure that we'll always get a fraction in return, so this one is always true. It will always be rational. Now here we have a rational number and an irrational number. We're taking the sum, so we're adding those together. So if we add a rational and an irrational, the result will be irrational. Well, so that means if we take a fraction and add it to, let's say, pi, well, they're not like terms, so we can't actually add them together, so the pi will always be there. So it will always be irrational. So this one is always true. Now the sum of an irrational number and an irrational number is irrational. So let's say we add pi and square root of 2. Well, that's going to be an irrational number. So that works. But what if we were to add, let's say, pi and negative pi? Well, that gives us 0, which is not irrational. So therefore, this is sometimes true. Let's take a look now at the Reasoning with Irrational Numbers review assignment. The assignment begins with the learning goals and success criteria. If we scroll down, we can see the questions. So the first one says, which of the following graphs represents the number on the number line? So square root of 2. What we should notice is square root of 2 should have two sides of 1. So this side would be 1, but this is really negative square root of 2 that we found here, right? This one comes from here, so this was square root of 2 here. So we went up a little more, so this is really square root of 3, so that's not correct. This one is not correct either. So this one here has a side length of 1, this side is 1, and then when we bring it down it's square root of 2, so it's D. And we'll continue to answer some of these questions. Then we're going to simplify some. So let's look at this one. It says negative square root of 54. Well, we should notice that square root of 54 is really 9 times 6. So we can pull out the 9, so that's negative 3 times square root of 6, which is this one here. So we'll continue to answer all of these questions until we get to the end. Once we get to the end, we'll click Next. This will take you to your Before You Go. Go ahead and fill out your Before You Go and then submit your work on Google Classroom.